Thanks, Matt. Power to you guys. We're in the home stretch here. I know this is a lot of information, and I have a picture of a very pretty K-cup, so you can just stare at it. It's colorful. Because I have the second opportunity, I want to apologize to Dr. Palmer. I contributed to one of his pet peeves in my earlier presentation, referring to humidity when I meant relative humidity, and I'm going to leave that to Ron to describe the difference, but it actually is very important. So I'm going to do my best to sort through the layers of precision agriculture, and it's such a beautiful layer cake. You know, is precision agriculture and variable rate technology just a beautiful, simple thing? Well, to be honest with you, I think, and I'm sorry for this, but variable rate technology, in my opinion, is probably one of the biggest under-delivered promise that agriculture has seen in the last 20 years. And it's not to say that it can't improve, but it's a really challenging task. So sometimes when I'm sorting through the layers, I have to cry. So I'm going to start by trying to simplify what it is that we're talking about when we're talking about layers in precision agriculture. And then I'm going to talk a little bit about a rather massive project that we have started off on. And hopefully we're going to make some sense of things and make some progress. The good news is that change is happening faster than it ever has. So if we're getting impatient with things, just wait a minute, it might get better. So one of the most important and first layers that I like to talk about is producer knowledge. Because farmers know their fields. And this is what they have for their tools. Sorry, guys. But really what it comes down to is you could take one of these crayons, whichever color you like, because you have 64 of them. And you could probably draw out where you think the variation is in your field. And you could probably do a pretty good job. The second layer I talk about is aerial imagery. This is something as simple as going to Google Earth and getting a free map off of Google Earth. Perhaps a georeferenced map is even a nice step forward. And a georeference just really means that you've got GPS, latitude, longitude coordinates attached to that map. No real data associated with these first two types of knowledge, but they are still knowledge nonetheless. So that's an example, and throughout this, I'm going to use the same field as part of a project that's up by Mossley. And you can see it's got some pretty defined lines, even just in an aerial map. So with gold, which was always my favorite ground color, you could draw in these very distinct ridge lines that you can see in the basic aerial photograph. And you can say, well, perhaps I have to manage that differently. The next layer, and this is a layer that we were focusing on our project, is a soil apparent electroconductivity mapping sensor. Sounds complicated, hey? Well, truthfully, it is. There are two types of sensors that are typically being used in agriculture. One is based on conductance and one is based on inductance. And Shelley Woods actually did a great presentation last year, and it's available on our website if you really want to dig into the difference of the two. So here's an example of an EM38 map of that same field. And at the same time, here's an example of a mistake using an EM38 field where apparently somebody went for lunch and came back and didn't recalibrate. So we've got this very clear line of difference. But you can still see those ridge lines that we saw in the aerial photograph. Another layer is a digital elevation model, the DEM. Sounds pretty fancy. Well, it is when you look at a pretty picture. So digital elevation model is basically that, looking at the topography within your field. And this has always been touted as a very important layer in precision agriculture, as it's going to have profound impacts on how the soil was formed and south-facing slopes and how moisture is moved. These maps are typically exaggerated so that we can literally see the difference. You can see there's a nice little peak up there. Remember that peak for later. There's yield maps. Now, I actually think that yield maps are probably one of the most underutilized pieces of information in agriculture, and I'm actually a really big proponent of us doing a better job using them. And this is the example of that, a raw, unfiltered yield map from the combine. And you'll notice in some of these slides, we're actually seeing some very unique patterns, and I'm going to describe to you later what we did with those patterns. But you can, even in the yield map, see some of those patterns that we saw in that original aerial photograph. Now, we can also look at some of these little neat gadgets back here, that helicopter that I want to take home because I could probably hook up my kid to it and take it for a ride. Or we've got this little airplane. Unmanned UAV-based sensors. Now, these are actually sensors that can fly over your field and give you rather accurate pictures that are both geo-referenced, and you can take IR pictures and come up with a digital NDVI map as well, and that's a measure of reflectance. And you can also create rather accurate digital elevation models using these sensors. And here's an example of a picture that was actually taken by Jan at the back here of our field in Mossley. Again, you can see the ridges very clearly as in the regular picture, but you can also see that we've been playing around rather dramatically within this field. Now we have satellite-based NDVI imagery. A lot of the precision ag companies are using this type of imagery. Essentially, we have different types of resolution, but it gives you a bioassay of the field. It's basically a measurement of the amount of chlorophyll that is seen from a satellite, and then they can take that and look at it over multiple years, say 10 years worth of it. So within all of these layers, there's basically ways of looking at the variability in the soil. But when I say bioassay, it's actually, okay, what happens when we grow something on that soil? And that's what this is based on. Here's an example of that same field of a Landsat image. This is an American satellite, and its accuracy is only about 30 meters. So you can see it doesn't give us a ton of resolution for what we're hoping to do with variable rate. But you can actually see those same ridges, even at that level of accuracy. What we were finding very much is that resolution in precision agriculture is rather important. Here's an example of a rapid eye image courtesy of Dale Steele and Farmer's Edge. Now this is a 5-meter accuracy NDVI map of that same field in the middle here. Now, with that improved accuracy, you can see, yes, we still see those very prominent ridge lines, but we're also able to see some of those treatment effects that we had our little experiment on. Number 8, and this is one that I apologize, I don't have an actual map for it, but ground-based vegetation centers. Some of you may have heard of Greenseeker technology. This is an on-the-fly sensor that creates another NDVI map. And we will have a map for this field because it so happens that the producer has his sprayer equipped with this Greenseeker technology. So it's just another type of map that can be produced. And finally, our last layer, and I may be missing layers, but I'm thinking that I've summed up sort of the sum of the different types of information that we can produce in precision agriculture. Ironically, and I've been doing some rough calculations, we've always been told that grid soil sampling is just too cost prohibitive. When I crunch some numbers on a 5-acre base grid, it's actually cheaper than a lot of some of these other types of layers. So this is some maps that were generated based on our grid soil sampling. On the left is the nitrogen map. Now, we're not actually seeing a ton of variability in that field, which is kind of interesting when we're trying to manage for nitrogen. And on the right is our phosphorus. For every soil test that you can have at the lab, you can create a map as well. So we've got organic matter on my left. It's probably, yeah, that's your left. And pH on the right. So now we have all of this information. I've completely clarified what precision agriculture is about for you, and now I'm going to just leave. No. Yeah, this is where the big trick is now. So we've got all of this information. What the heck are we going to do with it, and is it going to pay? And that's really what it comes down to. So myself in particular, I was very intrigued by a lot of these precision ag companies that were using these electroconductivity sensors as a base layer for their information in their agronomy businesses. Very cool. I actually had the opportunity to head down to a precision ag conference in the States, and the companies had a trade show, and I was looking at these various equipment, and electroconductivity is neat. One of the things that they're trying to look at is that how does that electroconductivity map relate to soil physical characteristics, things like sand, silt, and clay. And if we can use those to sort of predict what it is we're going to do with the farm, then it's another basis. On top of that, I noticed they had added on a couple of other instruments, an organic matter sensor as well as a pH sensor. So I was like, okay, well, this is a pretty neat fancy piece of equipment. So if I'm a farmer, should I just go hire a consultant because he's got this piece of equipment, or is there any truth or utility behind it? And of course, the EM38s they're an old technology. They've been around for many years. There's actually been a lot of research in southern Alberta using them for salinity mapping. So because this is such a complicated objective, we've put together a team of experts in various fields in precision agriculture, agronomy, soils, GIS, spatial statistics, remote sensing, salinity, economics, and I'm really seriously considering getting perhaps a psychologist too. Most of the data collection that we're doing is gathering all of those layers of information that I just talked about earlier. And then we're really going to focus in on the electroconductivity sensors because it's sort of a new thing in southern Alberta and in Alberta in general. So we're going to look at a number of fields. I'm not even sure how many fields we're at right now. But we're going to run these sensors across the field multiple times. And we're going to take the soil samples and see, is that correlation between the sensor data and the actual soil variability, is it a true and fair measure? And can we do anything with it? And we're taking a slightly different approach. We're going to do field scale replicated response trials. Then we're going to take all of those different layers of information and we're going to create zones based on those layers, and we're going to evaluate how well they correlate to true response, in a sense, after the fact. So I'm just going to show you a little quick video. I might shut it off earlier. But there was a lot of interest, and perhaps one of the reasons that precision agriculture has been sort of stagnated or slow to be, found useful, adopted, is that we haven't really put a lot of effort into researching it. We were very happy to receive funding to get to work on this. It's a very applied project, and a lot of guys are really interested in it. Within the project, we found out, precision agriculture is hard. And we're not going to be able to comment or help agronomists unless we're actually involved with it ourselves. So this project's given us the opportunity to dig in and find out what are the real barriers to adoption. And a lot of them are very real barriers and really tough. So in addition to the main project being funded through the funding consortium, we were able to secure a grant from the province, and you saw our MLA Bridget Pasteur presented us with a check so that we could buy one of these pieces of equipment ourselves and really sort of dig into it and discover the ins and outs and hopefully the benefits and clear up the mystery there. So the video that you're looking at right now is that Veris instrument. It's equipped with a soil organic matter sensor and a pH sensor. And then right behind it, we're towing a calf sled, and there's a dead calf in there. Okay, there's not a dead calf. That's where we house the EM38. But you'll notice right off the bat, there's a really difference in complexity between the pieces of equipment. The Veris machine is actually a lot more expensive, a lot more moving parts, a lot more maintenance. The EM38 is actually pretty simple in that regard. And this is a neat little camera that Morton at the back there mounted on so that we could take a look at that sensor moving up and down. And there's actually a water tank on there that you have to clean the sensor. It's a very complicated piece of equipment, quite honestly. And I think within our first field, those little sensors don't do well when you hit rocks. So our brand new machine, and here we are fixing it up. So after we run that sensor work, like you saw in the video, it's very important that we come and take the soil samples, and everything is going to be correlated back to that. So thanks a lot to the folks with Alberta Agriculture that have been participating in the project and helping us get some of these soil sampling done. This is just a quick shot of Chris here sorting it out. He's an expert. I think he could have got that back in the sheath a little bit smoother than that, considering his level of experience. But this was, you know, it's a very laborious thing, but it's actually really, really enlightening when you're trying to discover the true potential or the true worth or utility of the equipment. So the tins go in, and we have to get a proper calibration just on the moisture side of things, because we're looking to see, do these sensors correlate with moisture? Do they correlate with sand amounts and textures? So we're going to do gravimetric measurements there. And then from that, we're actually taking the test to the lab where we're doing the textual analysis. So we've got people that are busily doing that. It's very expensive to actually do this type of test, but then when we're done, we can plot the data and find out if there's actually any correlation. Now, again, like I talked to you earlier, we have a lot of work to be done on this. We're really just into our first year of this project. And this is when we've removed our outliers. So potential outliers would be salinity areas in southern Alberta. And this was the best correlation that we got. And we had to combine multiple fields to start to get this correlation. And basically what this is saying that is, as the silt content increases, our EM38 readings increase. And in this case, as our sand increases going along this axis, our EM38 rates are decreasing. So that's really the idea behind it. And it's also one of the main premises in variable rate irrigation, is that if you use these sensors, you want to know your sand, silt, and clay so you can determine your water holding capacity and come up with a prescription map as well. The sad thing is that any individual field, we weren't seeing much of a correlation. So I'm not exactly sure what that means, but it's something to think about. So I talked about a rather extensive treatment list. And this is a map of what we did on this one particular farm. And we varied our nitrogen rates from 0, 30, 60, 90, 120, but we also varied our seeding rate, about 250 to 350 seeds per meter squared. And it was a replicated trial across this entire field. And now you'll see that that map and the pictures that we were showing starting to make sense, because we're literally seeing, you know, a zero fertilizer treatment to a high fertilizer treatment. Physically, out in the field, we saw responses like this, where we had lodging in a very perfect straight line. The nice thing about doing this type of a treatment was that you pre-program it into your GPS software, and the farmer just seeds. As long as he's got a tank with nitrogen and a tank with seed, that entire research trial is just automatically adjusts depending on where they are. So very cool way to do research, and it's very simple and not too hard on the farmer as long as he keeps the tanks full. Within that, we're physically going out there, and all of these little dots along there are actually our stops where we took biomass samples. We weighed the biomass, dried the sample, weighed the sample, and then we actually threshed all of the samples out through our plot combine. And this was the one time that I actually went out and helped them, so I had to put a picture up. So here's our preliminary results on that first trial. And the good news is that he's seeing response to fertilizer as we move forward. The bad news is maybe we didn't go high enough. We have a bit of a blip in the data here where we're seeing a lower response on their 30 pounds. We still have to figure that out, but it looks like it's possibly that based on the randomization, it just so happens that this treatment had a few passes in the salinity area. So we haven't actually generated the data for our yield map, but it'll be very interesting to see how well it correlates to our physical work. This is our yield map though, and overlaid is our treatments. So we're going to use, we've got an expert in spatial statistics. We're going to go through, filter, clean the data, and come up with the actual field scale results and find out what we learn. Because we've got all of these different treatments across the entire area, this is where we're going to go after the fact. We can draw in our zones using those crayons in layer 1, and then we can do some real mathematical comparisons on which layer correlates the best, or which combination of layers. And that's all about verification. Notice in the top part here, even though we had different treatments, we're not seeing much for different responses. And sometimes that's the case. And you know what, given a type of year that we have, the environmental conditions, certain characteristics or certain layers may correlate better than others. Here is which I don't even know what it really means. Jody's been trying to explain it to me, but inverse distant weighted map of that treatment. And we're still seeing some very clear, distinct patterns within our treatment list. Now we go back to that color picture, and you can see how all of these different treatments are actually making a big effect. So in a sense, this demonstrates the potential utility of some of those layers of information. And back to our raw data. One of the things that we've learned very quickly is that in collecting some of these layers of information, GPS quality signal matters. So if you want to get an accurate topographic map or a digital elevation map, then you have to be careful in how you're collecting it. On the case on the left, this was the map of that particular field generated using RTK. Very clean, and this was that digital elevation model that was created based on that map. We could and should be able to generate that quality of a map based on the UAVs as well. But here's that same topographic map generated by GLONASS only. And GLONASS just does not have the horizontal accuracy that RTK does. And, sorry? Vertical. I always have vertical and horizontal mixed up. So this is the map, the digital elevation map. You can see that it's very different than this map. And that has significant consequences in the quality of data that you're going to have. So this is just sort of a rule of thumb. We always talk about horizontal accuracy, but to get effective vertical accuracy, we really have to get up to the high-end subscriptions, RTK or RTX. When you're down in the lower end subscription, you might as well forget about generating a horizontal or a vertical elevation map. That little peak that I mentioned that you should remember at the beginning, this is where it is, just to give you an indication of how high that hill was and the relief that we were dealing with. So here's some of the lessons we've learned in the year 1. Trying to do anything with ag GPS beyond auto steer is like herding cats. And this is really, you know, the hurdle that the precision ag companies have to deal with. And oh my goodness, it is really ridiculous. Auto steer is great. It's simple. It's easy. You want to try to do anything else, and it's like, yeah, we don't care. Leave us alone. We probably spent 100 hours trying to get our EM38 to communicate to our GPS unit simply because we had the wrong cable. And nobody could help us. Trimble couldn't help us. And it ended up being, we just finally stumbled across it. Yeah, you gave us the wrong cable. So there's a lot of technical issues within precision agriculture. And I think that's one of the hugest barriers to us doing anything significant with it. Within the EM38 and the Veris sensor work, calibration has been proven to be rather critical. So you really have to know what you're doing, and you have to be diligent in the calibration process, or the data that you're generating is useless. I mentioned the accuracy in GPS. I think in the sensor work and the elevation modeling work, accuracy, I think, is got to be something that we consider. Especially in comparing, say, the EM38 to a Veris, we need to use an accurate signal, and otherwise, you're collecting data, and if you've got a 7-meter accuracy, we're trying to relate it back to a soil sample, you could be way off, and you might miss some of the stuff you're trying to manage for. Things like constant speed, reasonable speed, spacing is important so that you have proper data. Soil moisture is important. if you don't have enough soil moisture, these sensors don't really work that well. And one of the challenges that we found, even in collecting data for this trial, is that we've actually got a really relatively short window to collect this data. I mean, to go at a reasonable speed, and we're doing 40-foot swaths, it's no different than us seeding. You know, even though we're pulling a little tiny instrument behind us, it takes us the same amount of time that it would a 40-foot drill to seed the entire field. Just a general comment, the Varus, as I mentioned earlier, more costly, but it also adds that value of an organic matter sensor and a pH sensor. And the truth is that the devil's in the detail, and it's really hard to maintain that focus. The more we dig into the precision agriculture, the more questions we have, sort of like John mentioned earlier, the unknown unknowns. A couple of quick shots. There's Jan retrieving his UAV. The octocopter stuff we've been playing with a little bit as well. I'm pretty interested in using this even for our plot work, so that we've got good aerial pictures. Autumn talked about the UCC. If we're analyzing our data and for some reason one of the plots is got a weird number, I can go back to that aerial picture and say, oh, gophers. This one I kind of like because our cooperator's reflection is in there, and he's scratching his head thinking, what the hell is he doing? And we had quite an experience. We were very excited that we got to lease a new piece of land at our Farming Smarter site. Unfortunately, it hasn't been cultivated for more than, I think, a year or two. We planted to canola, and it was a bad mistake because, well, this is the end of the presentation, so Mr. Gopher's thanking the Alberta Canola Producers Commission for making canola so tasty. And then ironically, we actually had to reseed about 50 acres to barley, which is also very tasty. So I just wanted to mention quickly, we have a new magazine, the Farming Smarter Fall Edition 2013 is out. If you haven't found it, it should have been inserted in the Alberta Farmer Express. It's also available on our website in a digital flipbook copy. And we would love to see you all back at our AGM. It's at Ag Expo. And as part of one of the issues in today's conference, we've missed out on a few speakers, and we really apologize for that, but we can't control the weather. But I was going to invite some of the speakers that were canceled at today's conference to come to our AGM at no charge. One of the things I wanted to do, and this was, want to know, some people were happy, maybe some people were mad, but if you could show me by a raise of hands, how many of you would actually like us to re-invite Mr. Huber? Can you, for the AGM?
Absolutely.
Okay. So what I plan to do is we're going to have Don Huber, Jan Salaski, and probably Merle Good for our AGM. And we'd love to come back and hopefully you'll get a chance to see them. So this is what I'd rather be doing right now. Thank you very much. Enjoy the rest of the conference.